Today, we're going to dive into a brilliantly elegant idea, the power of analogy, and how we can simplify some incredibly complex systems using a technique called lumped modeling.
All right, so this is the second explainer in our crash course on designing microsystems. In this one, we're going to build a really foundational tool that's going to let us analyze and understand systems that blend all different kinds of physics.
So, how do you even do that? I mean, how do you model a system that's part mechanical, part electrical, and maybe even has some fluids flowing through it all at the same time? It sounds like a total nightmare, right? But it turns out there's a surprisingly simple and really powerful way to tackle it. Okay, so here's how we're going to break this down. We'll start with why we even need to model complex systems. Then we'll learn a universal language of power before meeting the three basic elements that make up its vocabulary. After that, we'll uncover a kind of Rosetta Stone for physics. And finally, we'll put it all together and translate a mechanical system into a simple electrical circuit. All right, first up, modeling complex systems. Let's get to the core idea that really makes everything else possible. The hero of our story today is this concept, the lumped element. Instead of getting bogged down in every single tiny detail of a real-world object, we just simplify it. We treat it as a single, discrete thing that basically does one job. It exchanges energy with other things. It's an incredible simplification that lets us see the bigger picture. Now, for this whole idea to work across different kinds of physics, we're going to need a common language, a universal grammar for talking about energy. And this is where the magic happens. The core insight is this. It turns out that any time energy flows from one thing to another, that power flow can be described as the product of just two numbers. We call these conjugate power variables. So what are they? We call them effort and flow. Think of effort, which we call E, as the push or the potential behind a process. It's the driving force. And flow, F, is the movement or the rate that happens because of that push. So it's simple. You have something that pushes and something that moves. And this right here, this is the universal law in a nutshell. It doesn't matter what physical world we're in, electrical, mechanical, you name it, the power flowing into an element is always just the product of effort and flow. That simple equation, E times F, that's our universal language. Okay, so if effort and flow are our grammar, what about the words, the vocabulary? Well, let's meet the three basic elements that make up pretty much every system. Now, these probably look super familiar if you've ever touched electronics. They are, of course, the resistor, the capacitor, and the inductor. But the big idea here is that we can use generalized versions of these three components to build a model of any physical system. So what do they actually do? Well, a generalized resistor is anything that just burns off energy. Think friction. A generalized capacitor, that's all about storing potential energy, like a coiled spring. And the generalized inductor, that's for storing kinetic energy, the energy of motion, like a heavy mass that's moving. Okay, we've got our grammar, we've got our vocabulary. Now we just need the key that lets us translate between these different physical languages. We need our Rosetta Stone. And this is it. This table is our Rosetta Stone. I mean, just look at this. In the electrical world, effort is voltage, flow is current. We know that. But in a mechanical system, effort is force, and flow is velocity. And in a fluid system, effort is pressure, and flow is how fast the fluid is moving. See? It's all the same fundamental idea, just with different names. This is the key that unlocks absolutely everything. All right, enough theory. It's time to put this new language to use. Let's see what happens when we try to translate a real-world mechanical problem into a simple electrical circuit. Okay, so we're going to take a classic example right out of a physics textbook, a spring hooked up to a mass with something called a dashpot to add a bit of friction. It looks like a purely mechanical system, but is it? So let's walk through it step by step. First, we identify our parts: spring, mass, dashpot. Easy enough. Second, we look for their electrical twins using our Rosetta Stone. So what's each one's job? Well, the spring stores potential energy, just like a capacitor. The mass stores kinetic energy, the energy of motion, just like an inductor. And that dashpot? It just gets rid of energy through friction, which is exactly what a resistor does. And boom, there it is. That messy, mechanical spring-mass-dashpot system, it translates perfectly into a simple series RLC circuit, a resistor, an inductor, and a capacitor. This is that aha moment. We've literally turned a mechanical problem into an electrical one.
So why does this even matter? What's the big deal? Well, this quote really nails it. By turning our system into a circuit, we suddenly get to use this huge toolkit, things like Kirchhoff's laws and impedance analysis that engineers have spent decades perfecting for circuits. We can now solve our mechanical problem using the simple, well-known rules of electronics.
All right, so let's wrap this up. What are the big takeaways? First, lumped modeling is like a universal translator for complex, multi-domain systems. Second, all energy exchange, no matter where, can be boiled down to two things: effort and flow. And finally, pretty much any physical system can be built from just three equivalent building blocks: resistors, capacitors, and inductors. We just turn a mechanical system into a circuit, which is cool. But this way of thinking is way, way bigger than that. So I'll leave you with this question. What other really complex systems, I'm talking biology, economics, maybe even finance, could we understand better if we just learned to see them through this language of effort and flow?